All right, welcome back to another calculus lecture video. So in today's lecture, a little bit of a different lecture. What I want to do is just run through several examples of derivative calculations. If you would like, you can go print these notes yourself. The blank version is in the files section. So if you'd like to work through that on your own and then maybe check your answers with what I'll do here, I would encourage you to do that. But we've learned all of the differentiation techniques that I wanted to cover, and there are some other miscellaneous topics we could sort of touch on, but I think what we've done is certainly sufficient for any introductory calculus course. So without further ado, let's go ahead and just get into computing some of these derivatives. So for this first one, nothing too terribly complex. We've just got three terms, and so the derivative here is going to equal, well, it's just a sum of three things, so it splits up as the derivative of each one of these. And the examples that I'm going to do are by no means exhaustive, by the way. There are many other examples and many more I should do, but I just want to give a flavor of all the techniques that we've learned. So now we go through and we differentiate each of these. So I get 15x squared, applying the power rule. So I move my 3 down in front. 3 times 5 is 15, and then I subtract 1 from the exponent to get x squared. 20x, the derivative of x is just 1, so this is 20. And then the derivative of cosine is negative sine. And we're done. We're not going to do any more simplification than that. Okay, so for the second one, I have a product of functions. So I need to use the product rule in order to differentiate this. So let's do f of x equal to x squared, and g of x equals e to the x. So we're just going to give names to each of these, and then we compute each of them individually, or the derivatives individually. So f prime of x is going to be 2x. G prime of x is just e to the x. And so the product rule tells me that the derivative of a product, f of x and g of x being as above, this is the first, well, the derivative of the first function times the second, plus the derivative of the second function times the first. I think I normally say that in the reverse order, but it's immaterial. Addition is commutative. So now we just put in what each of these things are. So f prime of x is 2x, g of x is e to the x, g prime of x is e to the x, and f of x is x squared. So I'll be consistent and write it this way. Okay, and we could simplify this if we wanted to. This is e to the x times x squared plus 2x. Okay, so there's a quick product rule example. So moving on. So for this next one, I have a product and a chain rule that I'm going to have to do. I have an x squared inside of this exponent. So maybe let's go ahead and write down what our product rule will be first. So we'll let f of x be this sine of x function. G of x is going to be e to the x squared. F prime of x is cosine of x. And then now I need to figure out what the derivative of e to the x squared is. So in order to do that, we're going to apply the chain rule. Go ahead and make a space for it right here. So e to the x squared, I can think of this as, let's see, say h of x is equal to, so I'm going to let h of x be e to the x, and then j of x be x squared. So what I've done here is I've chosen my outside function, e to the x, and then my inside function as x squared. And what we're going to compute is the derivative of h of g of x. So we'll see that here in a moment. So the derivative of h is just e to the x. The derivative of j of x is just 2x. And now I have that the derivative, and I'm going to write it over here just to save space, so then d dx of, and what do I have? This e to the x squared, this is h of j of x, so this is h of j of x. This is equal to h prime of j of x times j prime of x. And then this is going to be, well, h prime of x is e to the x. And then in the exponent here, instead of writing x, I need to put in j of x, so that's my x squared. And then my j prime of x, which is 2x. And so this is the derivative of g of x, so 2x e to the x squared. That's exactly what we were computing in this step. And now we can combine everything together using the product rule. So d dx of f of x g of x is equal to f of x g prime of x plus f prime of x g of x. And now we just put in each of the pieces like we did in the last problem. So sine of x g prime of x, just put some parentheses around it to stay organized, f prime of x, and g of x. And again, we could factor out this e to the x squared, but not really worth it here. Okay, so there's a problem that involves both the product and the chain rule. Another way that we could have done this to maybe simplify our lives is we could have done logarithmic differentiation. I have a sort of complicated exponent and a product, and so maybe logarithmic differentiation would have also allowed us to compute this. Well, it certainly would have, and we would have gotten the same thing in the end, but maybe the computation would have been simpler. You know, maybe that's something you can try. But anyways, there are often multiple ways to differentiate something, and so it really doesn't matter which method you use so long as you end up with the right thing. Okay, so number 4 here, we have a quotient, so let's go ahead and apply the quotient rule. So again, we choose our f of x and g of x. We'll let f of x be the numerator, g of x be the denominator, and then these derivatives are quite simple. So f prime of x is just 5, because the derivative of 2 is just 0. It doesn't change with respect to x. And the derivative of 5x is just 5. You can also think of these functions as linear, and these are just the slopes of the lines. So g prime of x is going to be 3. And now what does the quotient rule tell us? So d dx of f of x over g of x, this is equal to, well, the bottom times the derivative of the top minus the top times the derivative of the bottom, all divided by the bottom squared. And now we just put all this information in. So g of x, and we'll be judicious with our parentheses, or generous, I don't know which word to use there. F prime of x is 5. F of x is 5x plus 2. G prime of x is 3. And then g of x squared is just 3x plus 1 squared. And we can simplify this a little bit. This is 15x plus 5. You distribute the 5 to each one of these, minus 15x minus 6. So there's a 3 times 2 here, which is giving me positive 6, and then the negative is coming from here, over 3x plus 1 squared. And the 15s, the 15x's, actually cancel out. So I'll actually have 5 minus 6, which is negative 1, divided by 3x plus 1 squared. Okay, and there is an example using the quotient rule. So this next one is kind of interesting. We could use the chain rule, or we could use logarithmic differentiation. I think maybe it's helpful to let's just do the chain rule on this one, because I think when you see things in the like odd expressions in the exponent, it's easy to get confused about this. So we'll do the chain rule again. So our outside function f of x is going to be 2 to the x. That is, the outside function is just the thing that I'm plugging the sine of x into, and that's 2 to the x. My inside function is going to be sine of x. F prime of x is the natural log of 2 times 2 to the x. Remember, we just take the natural log of the base and put it out front whenever we have an x in the exponent. And then g prime is just going to be cosine of x. And now we assemble what the chain rule tells us. So the derivative of f of g of x is equal to f prime of g of x times g prime of x. And this is equal to the natural log of 2 times 2 to the power of, and I plug in g of x here, so sine of x. And then g prime of x is cosine of x. And there's not really a lot of simplification we can do there. Okay, so there's a chain rule. Again, we could have done this with logarithmic differentiation as well. We would have gotten the same thing. So, and actually to show that this derivative, that these kinds of things, when you differentiate them in general, you in fact just use logarithmic differentiation to do that. Okay, so now let's move on to number 6 here. I've got a quotient, so I could use the quotient rule, but if I think about what the quotient rule actually says here, I have like the secant up here, I've times the 6x squared, and then I'm dividing by a power, and maybe it might actually be easier to just do logarithmic differentiation. So instead of having to apply both the product and the quotient rule, we would much rather just do logarithmic differentiation. So we'll convert all of these products and quotients into sums and differences, which we know is easier. Okay, so the natural log of this big thing my AC unit just kicked off and it seems very quiet now. Anyways, so the natural log of this, if we apply the properties of logarithms, this is going to give us the natural log of 6 plus the natural log of x squared plus the natural log of secant of x. Again, being careful not to make people laugh. And then minus the natural log of x plus 5, or x plus 1 to the 5th. And then we can further do some simplifications. So we have a natural log of 6, that doesn't change. The squared here and the x comes down in front. So 2 times the natural log of x plus the natural log of secant of x. And then minus, this 5 comes down in front, so minus 5 times the natural log of x plus 1. And now we're ready to differentiate this thing. So if I let this whole thing be f of x, then the derivative of f of x is equal to f of x times the derivative of the natural log of x. And this is going to be equal to f of x times, and now I actually just have to differentiate this whole thing. Oh, this is f of x. There we go. Sorry. Natural log of f of x. So now I need to differentiate this guy. This was the natural log of f of x, all in here. So let's differentiate this. The derivative of the natural log of 6 is 0. Natural log of 6 is just a number. 2 plus the natural log of x, that derivative is 2 divided by x, because the natural log of x just turns into 1 over x. Natural log of secant of x, this is, I put the function in the bottom, and then its derivative up in the top. So the derivative of secant is secant of x times tangent of x. and then minus 5 divided by x plus 1, and the derivative of x plus 1 is just 1. So that's why there's nothing else in the numerator. Okay, and we can simplify this a little bit. This is f of x times 2 over x plus tangent of x minus 5 over x plus 1. And we could sort of write down what f of x is. We could just put that right here, but we won't take the time to do that. I don't think that's necessary. So this is, I think, much easier than doing the product and the quotient rule together. It gets a little messy when you have to do both of those together and perhaps multiple times. I think this really simplifies the calculation. Okay, so now for this next one, I've got an implicit relationship between x and y. So I'm going to assume that y is a function of x and then compute the derivative using the chain rule. So we need to differentiate each side, so d dx of y squared minus xy is equal to, so if I apply the chain rule to this derivative here, I get 2y and then times dy dx. So I've just differentiated the y squared as if it was a function of x, and then I just make sure to remember to multiply by dy dx when I use the chain rule. To differentiate x times y, this is a product, so we need to use the product rule. So we have the first function times the derivative of the second plus the second function times the derivative of the first, which is just 1 in this case. So my second function is y, my first one is x, and I'm differentiating with respect to x. So that's the left-hand side of the equation. Now let's do the right-hand side, d dx of e to the x plus 5y cubed. So I have e to the x for the first derivative, that doesn't change. And then I'm going to get a 15y squared when I differentiate the y cubed, but then this is a function of, there's a y inside here, so I need to multiply by the derivative of y with respect to x. So let's go ahead and write down everything we have. So 2y times dy dx minus x times dy dx minus y, we have to distribute that negative. This is equal to e to the x plus 15y squared dy dx. And now what I'm going to do is get all of my dy dx's on one side and everything else on the other, so that way I can factor out the dy dx. So dy dx, or 2y dy dx minus x dy dx. I'm going to add the y over and then subtract this 15y squared dy dx. Okay, so I move the y over and I move the 15y squared dy dx over. And now I can factor out dy dx from each one of these terms, and I'm going to get 2y minus x minus 15y squared. And this is equal to e to the x plus y. And finally, in order to get dy dx by itself, I just divide by this expression. So dy dx is equal to e to the x plus y divided by 2y minus x minus 15y squared. And we're done. We don't need to do any more simplification than that. Okay, now for this last one, we've got the derivative of an inverse, so we need to use the inverse function theorem. That is just, the thing that tells us how to compute this derivative. So the inverse function theorem says that f inverse prime of 2 is equal to 1 divided by f prime of f inverse of 2. And then we need to sort of work our way out from the inside. So f inverse of 2, well, f of 1 is 2, and so if you apply f inverse on both sides of this equation, you get that f inverse of 2 is 1. So I have 1 over f prime of 1. And then I need to compute the derivative of f of x. So f prime of x is equal to, just apply the power rule, 3x squared plus 1. And so f prime of 1 is 4. So 1 squared is just 1, and then 3 times 1 is 3, plus 1 is 4. So this is equal to 1/4. And that's it. That's all we have to do. Nothing more complicated than that. Okay, so these were some examples of the derivative computations that show up in the online quizzes that I have for you all and in your written homework. Hopefully this was helpful, and again, I encourage you, if you want some extra practice, to get the blank version of these notes and work them out yourself. Okay, so see you all in the next lecture.